So today we are going to talk about some relationships between secant and tangent lines. So we got a little vocab to begin with. So if you take a look at the next page, first one is a secant. So a secant is a line that intersects a circle at 2 points, and that secant contains a chord. And then a tangent is a line that intersects a circle at only 1 point. That point that it intersects is called the point of tangency or the point of contact. So this is what this would look like. So you've got AB would be your secant, and then this would be your tangent. And let's say it's intersecting at C, that would be the point of contact or the point of tangency. Okay, so there's your first couple vocab words. Okay, next page. We've got two postulates, I should say. First one is that a tangent line is perpendicular to the radius drawn at the point of contact, and I'll show you a picture of that. And then the reverse is also true, where it says if a line is tangent or perpendicular to the radius at its outer endpoint, then it would be considered tangent. So this is what this would look like. So if you have a tangent line and you draw a line from the radius to the point of tangency, then it would be perpendicular. And then the reverse would also be true. If it's perpendicular at that point, then we can call it a tangent. Okay, next page. So next page has information about secant and tangent segments. So a tangent segment is the part of the tangent line between the point of contact and a point outside the circle. So this would be a tangent segment. And then a secant segment is similar, but it is the point just outside the circle to the farther intersection point. So this is what this would look like. So from A to B would be your secant segment. A to C would be considered your external part of the secant, and then this would be your chord because it is internal in the circle. Okay, next page. So then, I already kind of talked about this, but this is where it is. The external part of the secant is the part outside the circle, so we already talked about that here. Okay, then we have our first theorem, which is already typed up for you, so I'm just going to kind of describe it. But it's called the two-tangent theorem, and that is how we're going to refer to it when we use it in a proof. But it basically can be proven by hypotenuse leg. So if I have two tangent lines and they meet at a common point outside the circle, then they are congruent. And we can, prove it by hypotenuse leg because we know that these are perpendicular. We know that the radii are congruent, and then they share the hypotenuse. So that would be hypotenuse leg, making AB and BC congruent. All right, so let's see what this looks like in a proof. So in a proof, if you take a look at the picture here, based on the two-tangent theorem, we know that this is congruent to this because they're tangent lines meeting at a point. And we know that PR is congruent to PS for the same reason. So that was kind of my first step, second step, is saying that those are congruent. And then we have transitive property here, because if this is congruent to this, then this is congruent to this, then I can say that PQ and PS are congruent. So my next step was transitive, and that was really all that I needed. Okay. All right. Next one. So tangent circles are circles that intersect each other at exactly 1 point. Makes sense because tangent line intersects at 1 point. So this is the two ways that you could see it. So this, if the circles intersect at one point just kind of next to each other, it would look like this. Or you could have one circle inside the other. Now this would not be concentric circles because concentric circles share a center. This is what's called an external tangent, and this is what's called an internal tangent, which is described on the next page. So two circles are externally tangent if the tangent lies, if each of the tangent circles lies outside of each other. So this would be externally tangent. Internally tangent would be this one where one of the circles is inside the other. Regardless, in both cases, there's only one common tangent at the point of contact, and that point of contact lies on the line of centers. So in both cases, this line of centers is basically a segment that, or a line that goes through both centers of the circle, because that's going to become important in some of the problems that we do tomorrow. Okay. All right, let's draw. So I've got a couple more definitions, and I'm going to draw what this looks like. So a common tangent is a line tangent to two circles, not necessarily at the same point. That tangent is a common internal tangent if it lies between the circles, and it would be a common external tangent if it's not between the circles. So I'm going to show you what this looks like. So let's call this circle P, and this will be Q, and we'll draw our line of circles. So line of circles connects the two centers, or line of centers, sorry. XY would be a common internal tangent. So this would be what XY looks like. So XY, okay. And then AB is a common external tangent, would look something like, let's draw it here. So it would look something like that, because the internal goes between the circles, external does not. So that's what that would look like. All right, let's do some problems. So in this first one, I have that the radius is 10, so I know this is 10, I know this is 10. I know that these are perpendicular, which means that this is tangent, and I know that this arc is 60. So if the arc is 60 and this is a central angle, I know that this angle is 60, making this triangle a 30, 60, 90 triangle, and I am trying to find BC. So if I could find this whole segment, I could subtract out 10 and get BC. So I drew a 30, 60, I kind of redrew the triangle. So if this is 60, this is 30, I know this is 10. This is my A, 2A, A root 3. So then if A is 10, this is 20, so this is 20. And I just want this section, so 20 minus 10 is 10. So BC is 10. Okay. Let's try another one here. Okay. So on this one, I know that AB and AC are tangent to circle O, and since they're both tangent to the same circle and they meet at a point, I know that they are congruent. I'm trying to find that the radius, so I obviously need x. So if these are congruent, that means I can set them equal, and I can solve. So if I subtract 4x, add 15, I get that x is 12, but that's not it. I need to substitute in. So I substituted in and got 17. Okay. One more problem for today. So on this last one, we are talking about two concentric circles. So let's draw what this would look like. So we've got two circles that share a center. One has a radii 6, one has a radii 8. And we are finding the length of a chord of the larger circle. So larger circle chord, maybe something like this. And it is tangent to the smaller one. So here's the chord. It's a chord to the bigger circle, but it's also tangent to the smaller circle. So if it is tangent, then that point of tangency is a right angle, which means that this is also the radii. And so I drew it something like this. So I know that this is 8, I know this is 6, and then if I could find this, I can double it. So 6 squared plus x squared equals 8 squared. So 36 plus x squared equals 64. X squared equals 28. Square root, break this down. So that is 2 root 7. But I want to double that because I want the full length of the chord. So 7. So 4 root 7. All right, so we're going to stop here. And you've got a worksheet, so get to work on your worksheet, and then we will finish the notes tomorrow.